Okay, because I think my pencil is charged enough. Woohoo! And recording here, good. Not on mute, phew. All right. So I'm just going to keep adding to the notes from last day. All right, so we've got these notes here that we kept writing, and then so today we're just going to do 8.3 together, and I'm going to add a page here, and I'll say that today is March 30th, and I'll put a little box around it like I did last time. Okay. Assignment number 8 should now have a due date of March 31st at 11:59. Okay, so sorry it was closed. I closed last night instead of tonight, which I wasn't supposed to do. So I'm just giving a little bit of an extension there. And also, you should have received, or you should have, because I can never remember how to spell received, so you should have gotten an email from Gradescope. You should have gotten an email from Gradescope to see your test 2. Sorry that took so long for me to mark, but they're done now. Right, so if you have troubles, because I know there's a set your password, so people have been having troubles. If you have issues logging in, just like I said in my email, logging in, I added a blurb after the standard blurb. So if you have issues logging in, let me know. But also send an email to Gradescope. So send an email to help@gradescope.com. Okay, because they're the ones who should handle this. I don't have any access to your passwords or anything like that. So, so if you do have issues, then let me know. And I mean, I can always just send your test with the comments, but that would be very time consuming if I did it for everyone. So so just try the help at Gradescope and see what happens. All right. Checking for questions before we start here. Oh, yeah, thanks, Hannah. That's good. I made a list and I completely ignored it. The lab exam. So the lab exam is going to be on Friday. Okay, don't be scared. Lab exam is on Friday. Okay. It is going to be at 10. Okay, so that's different from, so not at our regular lab time. If that's a problem, then just let me know and we can have it at your regular lab time. But what everyone wanted to do was just to have all the lab sections right at the same time. So it's close to our lab time. But if you need to write in our regular lab time for whatever reason, because you work or I don't know. If you need to write in our regular lab time, then let me know. So it is just 50 minutes, 50-minute Moodle quiz. Okay, and I didn't have the whole practice test, but I posted a review document on Moodle this morning, which was prepared by another faculty member, but it's pretty good. It's very comprehensive, but really you've already been prepared for this this lab exam, with the exception of, I think, maybe 3 questions. C test 1, multiple choice. For practice, right? So it looks like what we're going ahead and doing is we're using my multiple choice. So a lot of these questions are my old questions. And so you'll see in the practice test, it's going to be very similar to our test 1 multiple choice. And so you've already seen a lot of these types of questions. So they're not going to be anything strange. And once I get those images and I'm able to compile it, that's for me, that's not for you. I will post a practice lab exam later today. So I couldn't get it to compile now this morning, but once I have everything to compile it, then I will post it with solutions. So it's going to be pretty heavy on the first test material, right? And so, things like what's the distribution, and should you use the mean or the median for the measure of center, all that fun stuff. So it is on Friday at 10, and it's going to be on Moodle. So if you have any concerns about internet access or anything like that, then just let me know, and we will work something out. Okay. All right, so checking for questions again here. Looks like we're all good. Okay, so I was really pleased with test 1 or test 2, so I will say nice work on test number 2. That was really good. I was really pleased with what you guys did there. So I'm happy with that. All right. So today we're doing the last section of chapter 8, which is, so section 8.1, just as like a tiny bit of review. Section 8.1 was 1 sample mean, sigma unknown. Section 8.2 was paired samples. Right. So that's when we're able to naturally pair. So we've got 2 samples, right? But they're paired, right? So these are 2 samples, but they're paired. So they'll behave differently than two independent samples, right? And so 8.3, oops, 8.3, two independent samples. Okay. So, in real life, I would say that two independent samples are going to be the most frequently occurring tests that you would run, right? So you're comparing two independent samples. Here I'll say we're comparing the means of two independent samples. So if we're comparing the means of two independent samples, then we're saying things like, oh, we've got the mean of group A and the mean of group B, and we want to compare and see if there's a difference in these means. Okay. So what we do is we do a two-sample t-test. Okay. So we're going to have a sample from each group. So we've got two groups that we want to compare, and we're going to take a sample from each group. So in terms of your data set, if you're thinking about you know, your Excel sheet or wherever your data is stored, you're going to have two columns of data, right? One column for your first sample and another column for your second sample. And from each of these columns, we would calculate a mean and a standard deviation, right? So each sample is going to have its own mean and its own standard deviation. I think it's a cool thing that these columns don't even have to be the same length, right? So as opposed to 8.2, where we're talking about paired samples, then of course our two samples have to have the same length, right? Because then we're looking at the pairs. But now, because we've got these independent samples, we can actually have different sample sizes for the two groups. So one important thing is the wording here. And so for matched pairs, right, what we're analyzing is we're analyzing the mean difference, right? So the average of the differences. The average of the differences, right? And how they compare to zero, and how it compares to zero. Whereas for two sample means, right, we're comparing, or we're analyzing the difference in the means, right? And so now we're talking about mu1 minus mu2, right? So this is the difference in the means. Okay. So that's going to be important, right? Because here, for the paired samples, right, we were talking about how mu d compares to 0, right? That was our null hypothesis. Our null hypothesis for matched, or for two sample means, sorry, would be that mu1 minus mu2 equals 0, right? If that's the case, oops, should extend to the 0, right? Two group means are the same, or essentially the same, or not significantly different. All those things mean the same thing, right? And so the two group means are the same if mu1 minus mu2 equals 0. Usually how I like to write it is just, or the same thing is saying mu1 equals mu2, right? And eliminating the 0. Okay. But that's just from moving the mu2 over to the right-hand side, right? Adding mu2 to both sides, we get mu1 equals mu2. Okay. So very important that we keep track of the wording. right? Because we're talking about the difference in the means, right, versus the mean difference. Okay? So now for this section, we're talking about the difference in the means, so how mu1 compares to mu2. The population mean of group 1, how does it compare to the population mean of group 2? Okay. So what we said was that we have two samples, right? And so we're going to have group 1, which is going to have a sample mean, a sample standard deviation, and a sample size. And then we're going to have group 2, which is also going to have a sample mean. So we denote it with these little subscripts 1 or subscripts 2, right? So X bar 2, S2, and 2, right? So each group is going to have its own information. Usually how I present this information is in a table, as we'll see in the example. Sometimes it'll be in text, but it gets pretty wordy. And so usually it'll be in a table, which will make it easier to identify when you have two independent sample means. So when we're talking about two independent groups, then our null hypothesis will always be mu1 equals mu2. So remember how I said that I liked paired samples because I knew what the null hypothesis was going to be? As soon as I've identified that I have two independent sample means, this is my null hypothesis. So this is always H0 for two sample means. I should have said independent there, but I don't have any room. And it's understood. So we are using subscripts for each of the groups. And what's important is that you use question-specific subscripts depending on what group 1 and group 2 are, right? For example, if group 1 is manatees, is manatees, and if group 2 is, I don't know, platypuses, right? Then my null hypothesis should be mu m is equal to mu p, right? So question specific subscripts. Because you don't want to use the general 1 and 2 because it can get really confusing. So you'll want to use these question specific subscripts, and I'll be looking for that if I'm marking your work. So like I said, you could either use this. I prefer this first one, mu1 equals mu2, because it eliminates, the need to remember the subtraction and the 0. So it's a little bit just cleaner looking to me. But you could use mu1 minus mu2 is 0, and then just have the equals 0. It doesn't actually matter. Both of these say the same thing, right? The null hypothesis is that the group means are the same for the two groups. And so that's our null hypothesis. Again, just like before, the not equal to sign is going to be our default in our alternative. Right, so our default is a two-sided test, but depending on the question, if you want to show that maybe manatees are faster than platypuses, right, then your alternative would have the greater than sign in your alternative hypothesis. The second thing that we would need is to do the test. So technically, you've got your estimate here, so x1 bar minus x2 bar. So that's the estimate of mu1 minus mu2. Okay. But what we'll say is, so we don't even have mu1 minus mu2, because from here, right, if mu1 equals mu2, then mu1 minus mu2 must be 0, right? And so on your formula sheet, I'm pretty sure it doesn't even have that second portion. Let me just confirm here. yeah, so here, the t on your formula sheet is just x1 bar minus x2 bar. Technically, it would be minus mu1 minus mu2, but that's always 0 because that's our null hypothesis. So same as for the paired samples, right? This is going to be our t that we calculate. We can also see here that we've got these degrees of freedom. So let's talk about those. So it's a little bit more work, right? Calculating your t. But once you have your t, then everything's kind of hunky-dory, right? Because then you're back to the t table. You'll need your degrees of freedom, which we'll talk about here. But once you have your t, the t behaves the exact same way that it has been doing. So you've got your sample mean 1 minus sample mean 2 over the square root of the standard deviation of group 1 squared over the sample size of group 1 plus the standard deviation of group 2 squared over the sample size of group 2. Remember, you have to square these, and then don't forget to take the square root, right? So you'll want to be really careful when you're showing your work here that you're not missing a step. Okay. So what we're doing is we're seeing how far the sample means, the difference in the sample means is from 0, right? And if they're not significantly far away from 0, right, the difference, then there's no significant difference between them. Okay, so technically, to find your degrees of freedom, you should use this. We are never going to use this. We will never use this to find the degrees of freedom, right? Since R or any software can do this calculation for us, what we do is we use a more conservative approach for our hand calculations. So if we're doing it by hand, right, then we use the minimum of n1 minus 1 or n2 minus 1, which is essentially saying use the smallest sample size minus 1. Okay. So if you've got 2 sample sizes, right, if we just kind of zoom ahead to the example, we don't have to read it quite yet, but we've got a sample size of 30 and a sample size of 23. Our degrees of freedom should be the smallest sample size, which is 23, minus 1. And so that's all this is saying. Once you have your t that you've calculated, you know your degrees of freedom, then you're on the t table, and how you draw the conclusion is the same as for all the other hypothesis tests, right? So if the p-value is small enough, so smaller than the alpha level, then you have enough evidence to reject H0 in favor of HA, and then what does that mean in terms of the question? So I'm going to check for questions here, but I don't see any. Okay. All right. All right. So let's do an example. So this one is one of those that's typed up, just so we can see the flow, and then we'll do one together, and then we can move on to confidence intervals. So as you've noticed probably now, right, when we're talking about these different types of problems, so all we're doing in each of the sections from here on out is we're just introducing a new type of problem, and I'm showing you how to do a hypothesis test and then how to do a confidence interval for each of those types. And so we're slowly plugging away at the formula sheet. If you look at your formula sheet, so here this first section is for confidence intervals for means and hypothesis testing for means. Okay. Next day, we'll start talking about proportions, right? So we can do confidence intervals for 1 sample proportions or 2 sample proportions. So they look a little bit different. And then same thing, hypothesis testing for 1 sample proportion or 2 sample proportions. And you guys are in luck because we've decided to cut the chi-squared goodness of fit testing. So we're not going to do that this term. That's okay, we will survive. So we're not doing chi-squared, that's just chi-squared. Chi-squared this term. So what we're going to do, right? So today we're talking about 2 independent samples. Next day we'll talk about 1 sample proportion. The following day we'll talk about 2 sample proportions, and then we'll be done. So, all right, let's see here. So here's our example, kind of a fun example. So the weights of diamonds are measured in carats, in case you were unaware. The difference between the size of a 0.99 carat diamond and a 1 carat diamond is undetectable to the naked human eye. So, but does the price of a 1 carat diamond tend to be higher than the price of a 0.99 carat diamond? So we're going to test to see if there's a difference between the average prices, right? So we're testing the difference between 2 averages of 0.99 and 1 carat diamonds. So just some background on what they did for the math. So in order to be able to compare the equivalent units, and this is not something that I would get you to do, this is something that I would tell you has been done. So we divide the prices of 0.99 carat diamonds by 99 and 1 carat diamonds by 100 to compare the average point prices, right? And this is just to make our analyses kind of more clean looking. So you collect 2 random samples of diamonds, 1 sample of 1 carat diamonds and 1 sample of 0.99 carat diamonds. And what we find is the following summary statistics. First thing we're going to talk about is we have 2 samples, right? We've got 1 carat and 0.99 carat diamonds. And so the question is, are they paired or independent? Right, so that's the first step that you have to use as for yourself when you're reading all these problems, right? You're gonna have to ask yourself, are these paired or independent? They're independent, right? Because there's no natural way to match 1 carat or 1 diamond, sorry, 1 diamond to another. And that's okay. Like I said, this scenario is actually the most common one, right? It's the last one that we go through because it's, as you've seen, it has the biggest calculations and things like that. But at the end of the day, most of the time, we are going to be dealing with independent samples. Another clue is that we have these different sample sizes. Also, different sample sizes means we have independent samples. So look at the information that I've given you here, right? I give you the mean of each of the groups, the standard deviation of each of the groups, and the sample size of each of the groups. If I wanted you to treat this as a paired samples test, then I would have to give you the mean of the differences as well, right? So there would probably be another column here with the differences, and then we would have the differences of the mean difference, the standard deviation of the differences, and the number of the differences, right? And so how you are given information about the problem is going to kind of lead you one way or another, right? In this case, we have independent samples. So the question is there evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? Okay, so first thing we have to do, right, is we have to set up our null and alternative hypotheses, right? So what we'll do is I'm just going to define group 1 as the 1 carat diamonds and group 2 as the 0.99 carat diamonds. What you'll see is I got lazy, so I only use the specific subscripts, right? And so here, these are question-specific subscripts. But what you'll see here is that I got lazy and used the general subscripts. Right. But with the groups defined above. So you do have to tell me, right, with the groups defined up here. So you do have to tell me which group you're treating as group 1 and group 2, and I want to see question-specific subscripts in your null and alternative hypotheses, right? In this case, we have to assume that the mean point prices for each of these groups is the same until maybe we have proof that the mean of the 1 carat diamonds is higher than the mean of the 0.99 carat diamonds, which is what we're kind of hypothesizing here. So, but then here, right, because it can get kind of messy with 0.999, or so 0.99, yeah, that's what I said. I just use 1 and 2 as long as I've defined them up above somewhere. So what I do is I take the information from here, right? So now I'm calling this group 1 and this group 2. So my X bar 1 is 53.43, my X bar 2 is 44.5, et cetera, et cetera. And even though it's a big, nasty calculation, right, it will just boil down to a t that we know how to deal with. So we plug in our numbers, and as long as we're careful, right, making sure you square those standard deviations, and then finally take the square root in the end, right, you should get up to 2.507. So just looking at a t of 2.5, right, I suspect that I'm going to be rejecting the null hypothesis, right, because this is larger than 2, a plus or minus 2, and so I already suspect that I'm going to be rejecting H naught. But we have to keep going to the third step where we find the p-value, just to have some backup or some proof. So what we do is, I'll make this bigger here, we have to find the p-value. So using the t-table, so now we use the exact same, this blurb is the exact same as what we've been using for the previous 2 sections, right? So you tell me that you're using the t-table, and then the only difference here is how you find the degrees of freedom. The degrees of freedom is the minimum, and this is exactly from your formula sheet, the minimum of n1 minus 1 and n2 minus 1, which for us, if we substitute n1 and n2, which is 30 and 23, right, we get to the minimum of either 29 or 22. The minimum of 29 or 22 is 22, right? So that's our degrees of freedom. Same as before, right? If you get a degrees of freedom that's not on your table, you always have to round down. 22 happens to be on the table, so that's fine, right? But if this was 82, you would have to round down to the nearest degrees of freedom, which I'm pretty sure 80 is on there, but so you'd have to round to 80 probably. So then, same setup, right? You've got your calculated t. So this is the one that goes here, right? In the absolute value brackets, just to make sure that if you've got a negative, then it goes away. So if we go to our t table with, with 22 degrees of freedom here. This is the line that we're on. Okay. Then I'm trying to place, what was my value? 2.507. I'm trying to place 2.507 on this line here, moving out 2.508. Oops, stop. Somewhere between here and here. Right. So here I've got 2.507, right? It's somewhere between there and there. 2.183 and 2.508. At first I need to write those down. And so 2.183 and 2.508. Okay. Then going back to the table, right? Oops. Am I looking for a one-sided or a two-sided p-value? In this case, I'm looking for a one-sided p-value, right? And that's because, and it's between 0.01 and 0.02, I need a one-sided p-value, which happens to be between 0.01 and 0.02, because if you go back to your null hypothesis and your alternative hypothesis, right? Because I've got this greater than, I'm only concerned with one side. So this is a one-sided test, oops, which means we need a one-sided p-value. Right? So that's why we're using a one-sided p-value. And I know that that can be tricky. I know a lot of people have trouble trying to figure out if you have a one-sided or a two-sided test, because it stems from the beginning, right? The alternative hypothesis. So now our one-sided p-value we know is between 0.01 and 0.02. We know the one-sided p-value is less than 0.02, so it's definitely less than 0.05, unless we were given a different alpha level. We're going to use 0.05. So since our one-sided p-value is between 0.01 and 0.02, okay, it's less than our assumed alpha level of 0.05, right? And so here, kind of from here, we use the exact same layout as before. So one, the first thing you have to do is you have to compare the p-value to the alpha level. Okay. Next thing you have to do, which means we have enough evidence to reject H0 in favor of HA. Second thing you have to do is tell me what the conclusion in terms of H0 is. Okay, so that's going to be important because we do all our testing assuming H0 is true, right? And so your conclusion has to be either you reject H0, and if you do, you can say in favor of HA, or you don't have enough evidence to reject H0, and then that's it, right? And then finally, don't forget, this means that there is evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds. That's your conclusion in terms of the question. Oops, conclusion in terms of the question. Right, and so your conclusion is long, right? But that's because it's got these 3 parts, and you have to touch on all 3 parts to get all the marks. And also, otherwise your research would probably not be accepted. So there's always that. So, all right. Okay. So we've got our conclusion. So we found a small enough p-value, so we had enough evidence to reject H0, which means that there is evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds. So it's not up to us to decide what people should do with this information. This is just the fact. And so that's kind of a classic statistician thing, right? Is we just say, here's what the data says, do with it what you want. But if we were pressed, right, and it kind of depends on where we're coming from, right? Are we selling diamonds? Are we buying diamonds, right? That makes a difference. But let's say we're buying diamonds, then how would we use this? Well, I would probably, I'm guessing I would probably buy the 0.99 carat diamonds because I can't see a difference between a 1 carat and a 0.99 carat diamond, right? But it turns out that the average point price is significantly less, right? That's the reverse of the 1 carat diamond being significantly higher than the average point price of the 0.99 carat diamond. Okay, so I'm gonna check for questions here, but I think I see none. Okay. So I prefer to spend our time working through this example together and then leaving the confidence intervals. But what I'll do is I'll go through the worked out confidence interval, and then if need be, then I'll just post the solutions, or I'll add the solutions in the notes here before I post them, just like I have been doing. So if we run out of time, then work through it on your own and then check the notes for the solutions. So let's just talk about the confidence intervals. And it follows the same, so a confidence interval for the difference between 2 means follows the same type of structure, right? We use the same information as we did before. So we've got x1 bar minus x2 bar. That's all given in our kind of sample information. S1, S2, N1, N2, all of this information besides the T star is all from the original question, right? So we could easily do a confidence interval and the degrees of freedom stays the same. Could easily do a confidence interval for the diamonds, right? What would that tell us? If we did a confidence interval for the price of the diamonds, right? The price of a 1 carat diamond minus the price of a 0.99 carat diamond, it would tell us how much higher the average point price is for each of these carats. So if we made a confidence interval for the diamond example, we would find how large the difference in the average prices is. How large the difference in the average prices, or in the average price is. Okay, so that's the difference between a confidence interval and a hypothesis test. A hypothesis test tells us that there is a difference, right? Whereas a confidence interval tells us, you know, how large is that difference. So what I'll put in summary here, I'm sure it's in the notes somewhere here, but a hypothesis test, is there a difference, right? Yes or no? Whereas a confidence interval says, okay, well, what is the difference? So like I said, kind of modern statistics focuses on the confidence interval because we can use, okay, well, if we know what the difference is, then I can compare it to 0. And if it's not 0, then there must be a significant difference, right? And so we can kind of do everything that we need using confidence intervals, but we're, you know, sticking to the old school ways, and we're doing a proper hypothesis testing procedure. So kind of an interesting study. I'm assuming it was done in Israel because the amounts, the money amounts are in Israeli shekels. So obviously I just stole this from a textbook sometime. So when the time comes for a group of people eating together at a restaurant to pay their bill, sometimes they might agree to split the costs equally, and other times they will pay individually. If this decision is made in advance, would it affect what they order, right? And so is the mean price of what they order going to be dependent on if they decide to split the bill beforehand, or if they're going to pay individually? So some researchers conducted an experiment where 48 Israeli college students were randomly assigned to eat in groups of 6. So 3 females and 3 males, just to kind of keep it interesting, I guess, no, to keep it even. So before ordering, half the groups were told they would be responsible for paying their meals individually, and half were told to split the cost equally among the 6 participants. The 24 people paying individually had a mean cost of 37.29 Israeli shekels, with a standard deviation of 12.54, while the 24 people splitting the bill had a higher mean cost of 50.92. So that's the average cost per person, Israeli shekels, with a standard deviation of 14.33. So here, this is another way that I could give you all that information, right? We've got the sample sizes, and here the sample sizes happen to be the same, right? But it's got a mean for group 1, a standard deviation for group 1, mean for group 2, and a standard deviation for group 2. So N1 is 24, X1 bar is 37.29. Actually, haha. I've even got it in the notes, so I'm not going to bother. Right. So here, we're given all that information there. So both distributions are reasonably bell-shaped. That's just to satisfy our conditions here, which we haven't really been paying attention to for testing means. We will pay attention to it for proportions next day. So what I've done is I've decided that group 1 is going to be the group paying individually, right? Because that was the first group that appeared in the blurb, so it just is easier. Group 2 is the group splitting the bill, second group that appeared in the blurb. And so we need to find our T star, so we need to find our degrees of freedom. It's the minimum of 23 or 23, which is 23. And using the T table, we find that T star should be 2.069 for a 95% confidence interval, because we want to construct a 95% confidence interval for the difference in mean cost between these two situations. Again, quite a bit more math, right? But as long as you kind of break it down and do each of these individually, right? Follow the steps that I've outlined here. Make sure that you get to the same value, right? The difference in the average price per person is going to be between -21 and -5. 59, I guess, negative 2167 and negative 559. Same blurb as always. We're 95% confident that the interval from negative 2167 Israeli shekels to negative 559 Israeli shekels captures the difference in mean cost between these two situations. Okay. So that would be kind of the end of our interpretation. But here, right, as this interval is consistently below 0, and we analyze individual minus, so paying individually minus splitting, we can say that splitting the bill consistently yields a higher average, right? Because that's how we would get these negative numbers, right? Because what we said was, we said x1 bar minus x2 bar, which is paying individually minus the splitting the bill, right? So if this is negative, well, that means that individually is less than splitting, right, consistently. And so we can say that splitting the bill consistently yields a higher average cost, right? Or the individually yields a consistently lower cost than splitting, and those are, you know, inverses of each other. So splitting the bill consistently yields a higher average cost than paying individually. In fact, we can add here on average, splitting the bill means the average cost will be 559 to 2167 Israeli shekels higher. Or if you want to phrase it the other way, on average, paying individually means that the average cost will be 559 to 2167 Israeli shekels lower. It really doesn't matter how you phrase it. They mean the same thing, right? So I suspect that we won't really have time to go through this confidence interval example because I want to go back and do that hypothesis testing example. But I'll post the solutions to this one before I post the notes. Okay. So I'm going to add a page here because I know I'll need it. Yeah. So let's go back to example 10. So a study examined the impact of the color red on how attractive men perceive women to be. In the study, men were randomly divided into two groups and were asked to rate the attractiveness of women on a scale of 1, not at all attractive, to 9, extremely attractive. One group of men were shown pictures of women on a white background, and the other group were shown the same pictures of women on a red background. Right? So the only difference is the color of the background, and the results are recorded below. So it looks like the red background, right, had a mean score of 7.2, whereas the white background had a mean of 6.1. And just to satisfy the conditions, which I'm not really concerned with for you guys, the data for both groups are reasonably symmetric with no outliers, right? So you can ignore that, sort of. Is there evidence that the men who saw women on the red background rated them as more attractive? Right, and so what we can say is that 7.2 is higher, right? That's a fact, is higher than 6.1, but is it significantly higher? right? This is where we have to do a hypothesis test. In general, as soon as you see is there evidence, that means you have to do a hypothesis test. So, all right, here we go. Step one, well, actually, step 0, right, is figuring out what type of question we have. Because if you're looking at a bunch of different questions, then the first thing you have to do is identify what type of problem this is. So I want you to add in step 0, which is the question type. Right? First clue is how I've presented the data, right? Even without reading anything else, right? I see that there's a mean for group 1, a mean for group 2. There's no mean for the differences between the two, so I'm thinking two independent sample means, but which is confirmed with the 2 different sample sizes, right? That's not always going to be the case, right? We often have the same sample size, but that just confirms it. So this is 2 independent sample means. Because we're comparing 2 independent groups. So step 1 is to state the hypotheses. Your null hypothesis, remember, is just always mu1 equals mu2. Right? But we want question-specific subscripts for hypotheses, at least. Right. And so what I'm going to do is I'm going to have H naught is that, and usually I just do them in the order that they appear, is that the mu for the red background is equal to the mu for the white background. Okay. So what I'm going to do is I'm just going to write a little bit below here, let group 1 be the red background and group 2 be the white background. Okay. We want to know, is there evidence that the men who saw women on the red background rated them as more attractive, right? So meaning, is the red mean higher than the white mean? So we've got a one-sided test again. And so I need to reflect that in my alternative hypothesis. My alternative hypothesis is still going to be about mu r, how it relates to mu w, but I want to know if mu r is larger than mu w. So this here means I have a one-sided test, which means I'm going to need a one-sided p-value when I get there. Okay. So we've got our hypotheses, right? Here's the default mu1 equals mu2. That's the one I like. You could use mu1 minus mu2 equals 0, but I just find this one cleaner. So then mu r equals mu w, right, after we incorporate our different groups, right, our group-specific subscripts. And then, so our alternative hypothesis, this is what we think might be going on, right, but we have to assume that they're the same until we have proof otherwise. So now in step 2, we do the test. So doing the test, we've got T, and we'll steal it from your formula sheet, right? Because we're doing a hypothesis test, so we've got 2 independent samples. Again, it's got that null hypothesis on there if you need it. And I'm just going to cut this, copy, and paste. Okay. So here, right, because I've identified which one is group 1 and which one is group 2, I'm not going to use little r's and w's in here. It gets really messy, so don't worry about that. I'm only concerned about that in your null and alternative hypothesis. So we've got x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. Here, you really want to make sure that you've got a handle on your calculator, how it works, right? Make sure that you get the same numbers that I do. x1 bar, let's steal it here. I'm just gonna, copy, just so we have it and we can plug it in. x1 bar is 7.2 minus x2 bar is 6.1, right? Making sure that you keep track of which group is which. This is group 1, this is group 2. So then we've got S1 is 0.6 squared over N1, which is 15, plus S2, which is 0.4 squared over N2, which is 12. Right. So now, slowly but surely, we're going to work through this, right? You have to start, so you can simplify the top. The top and the bottom you can simplify independently, so simplify the top, but then start by squaring your standard deviations and then dividing those by the sample sizes, then adding them together, then taking the square root. So I have 7.2 minus 6.1 puts me at 1.1 over, and I've got 0.6 squared is 0.36 over 15 plus 0.4 squared, which is 0.16 over 12. Maybe I should use a different color to indicate all the changes that I've made. 0.36, 0.16, just so you can see. So now 1.1 stays the same, and I've got the square root of, so now 0.36 divided by 15 is 0.024 plus 0.16 divided by 12 puts me at 0.0133 repeating. You want to keep all those decimal places, right? And so what I'm going to do, because I've got this on my screen on my calculator, I'm going to add 0.024. Or if you've got two large numbers here that you're dealing with, right, large in terms of the number of decimal places, then I would probably store these numbers. You want to keep all those decimal places, right? So now 0.0133 plus 0.024 puts me at 1.1 over the square root of 0.0373 repeating. Okay. Again, keeping all these decimal places in here, and I'm going to take the square root next. So I get equals 1.1 divided by, take the square root of that guy, I get 0.19321835566. And probably keeps going, right? But my calculator caps out at 9 decimal places or whatever. So now if I do 1.1 divided by that guy, I get roughly 5.693040.865 t, right? This is my t from way back here. This is all the t that I'm arriving at. I get a t of 5.693040.865. T gets rounded to 3 decimal places, 5.693, and that's 3 decimal places to match the t-table. Okay. We have to have 3 decimal places. Okay, so that's step 2, calculating the t. Quite a lot more work, right? One thing to notice is that, remember, if you look at your confidence interval, I'm not going to bring it up because I want to show this here, but the confidence interval uses this whole chunk, okay? If you've already done the calculation once, then show me that this is what you would use, and then you can skip straight to here where you've solved that huge square root. Okay, so if you've done a calculation once, then you can just write me a note and say, hey, I found this in part A or whatever, and I know that it should be this. Okay. So now we're ready for step 3, sorry. Step 3 is find the p-value. Same blurb as before. Let me see here, add a page. Using the t-table, well, what do we need to use the t-table? With degrees of freedom equal to the minimum of n1 minus 1 or n2 minus 1, which is, in our case, right, so this is exactly from your formula sheet. Now we fill in n1 and n2, which is the minimum of n1, which is 15, and n2, which is 12. 15 minus 1 or 12 minus 1, which is the minimum of 14 or 11. The minimum of those is 11. Okay. And I guess we usually say something like, we find, and so here, right, I use the same setup always. The absolute value of the t that I calculated, 5.693, is going to be between 2 values. This is fairly large, right? 5.693 is really large. And so it might be that it's kind of off the charts. So let's go see here. I said I have, what degrees of freedom? 11, I think. So if I have 11 degrees, let me just check to make sure that that's what I said. 11 degrees of freedom and 5.693. So 11 degrees of freedom. What I'm finding is that 5.693 is somewhere out here. Right? All I can say is how it compares to 4.437. So what I have to do here is that that's larger than 4.437. Okay. Technically here, we would have infinity, right? These t's, the z's, the t's, they all go to infinity, right? Or we can write 4.437 is less than the absolute value of t equal to 5.693 and just ignore that infinity. I like to have something on both ends, and so 5.693 is definitely less than infinity, so this is true, it's just not very helpful, right? And so, which means, and remember, we need a one-sided p-value because we had a one-sided test in our alternative hypothesis, right? We've got a one-sided test because I only care about one side. And so here, I need a one-sided p-value. If I go back to my table, well, my table tells me that the p-value, the one-sided p-value for 4.437 is 0.0005. Now remember, we have to do the switcheroo here. So the one-sided p-value is less than 0.0005, right? but greater than technically 0, right? And so, or we can just say that the one-sided p-value is less than 0.0005. Either way, just because our t is super big, right, 5.693, our p-value is going to be really, really small. So I know I'm going to be rejecting H0. It's just a matter of communicating how small the p-value is. And I know I'm out of time here, but I'm ready to do my conclusion. And so step 4 is our conclusion. First thing I have to do is compare my p-value to my alpha level. Since our one-sided p-value, I like to show off that I know that I need a one-sided p-value. Our one-sided p-value is less than 0.0005. It is also less than our assumed alpha level of 0.05. And kind of splitting it up here, which means we have enough evidence to reject H0, in favor of HA. So here, right, this is our first part of our conclusion. Here's our second part of our conclusion. And then finally, I would argue the most important part of your conclusion is what that means in terms of the question. The question was, is there evidence that the men who saw women on the red background, so copy, rated them as more attractive? Well, what we're finding is that yes, there is. Oops. Undo, paste image. So what we do, we just rewrite the question as an answer. There is, or I guess I should say, therefore, there is evidence. Now we just rewrite this question as an answer, that the men, and there are times when the question is worded funny, so, but just, you can just use the same tactics always, right? Just rewrite the question as an answer, even if it's worded, strangely. I'm not too concerned about that. I trust that you'll be able to word it better if you make up your own research question. So therefore, there is evidence that the men who saw women on the red background rated them as more attractive. So what are we going to do? All our Instagram posts should be on a red background. Haha, I almost used red, even though I should be using green to match my layout before. All right. So what we do is just reword question as an answer. Haha. All right. So what I'll do is, so there's our whole question. It's a lot of work, right? But hopefully what you're finding is that there is a rhythm, there is, procedure that we follow for all these hypothesis testing questions. And so for that reason, I like it. I like monotony, but I know. I will fill in the solutions to this last confidence interval, but have a go and see how it goes. And make sure you get the same answers that I do. And yeah, that's good. So next day, we're going to start talking about proportions. are there any questions before I let you go? No questions. Give you a little bit of time to type them out. But otherwise, I'm going to boot us all out. Sorry, Manuel.
No problem.
Showing up early. Awesome. Thanks, guys. Quote unquote. See you on. Ruben. So there is the lab final. The lab final is on Friday. I posted a review document on Moodle. Is there anything beyond that? No. We're taking things as they come. I know, not the best, but I was really pleased with your guys' test too. So make sure that you're able to see those. No, so the lab final is not the final, but rumor has it that they took down the final exam times. No, there will be, just for the record here, there will be, I guess I should use kind of quotes, a real final online somehow. Yeah, what a gong show. So there will be a real final, but the lab final is just gonna basically be the short answers of it, so don't worry about it. But all right, cool. Interesting times indeed. Yeah, see you guys later. I know, it's the worst. See ya. Mm-hmm.